Hello, my name is John Moyer, and I want to welcome you to the NIH Office of Disease Prevention's Mind the Gap webinar series. This series explores research design, measurement, intervention, data analysis, and other methods of interest to prevention science. Our goal is to engage the prevention research community in thought-provoking discussions, to promote the use of the best available methods, and to support the development of better methods. Before we begin, I have some housekeeping items. You can submit questions during the webinar via the chat pod. You'll need to open the pod by hovering your cursor at the bottom of the Zoom window and then clicking on the chat icon. Please direct your questions to hosts and panelists. We will open the floor to questions that have been submitted via the Zoom chat pod at the conclusion of today's talk. The slides and video recording will be posted on our website, prevention.nih.gov/mindthegap, in a few weeks. Lastly, we would appreciate your feedback about today's webinar. Upon closing, you will be asked to complete an evaluation. We would appreciate your feedback as it will help us improve this webinar series. At this time, I'd like to introduce our speaker, Dr. Emily Tanner Smith. Dr. Tanner Smith is a Thompson Professor in the Counseling Psychology and Human Services Department at the University of Oregon. She is also the Associate Director of the University of Oregon's Prevention Science Institute and Executive Director of the HEDCO Institute for Evidence-Based Educational Practice. Dr. Tanner Smith's research focuses on meta-analysis and research synthesis methods for evidence-informed decision-making, with specific emphasis on the prevention of academic, behavioral, and mental health challenges among youth. Dr. Tanner Smith currently serves on the editorial boards for Psychological Bulletin, Prevention Science, and Research Synthesis Methods. Her meta-analytic research has been funded by numerous sponsors, including the Institute of Education Sciences, the National Institute on Drug Abuse, the National Institute on Alcohol Abuse and Alcoholism, and the Office of Juvenile Justice and Delinquency Prevention. In honor of her research synthesis contributions to prevention science and public policy, Dr. Tanner Smith received the Nan Tobler Award from the Society for Prevention Research and the Robert Baruch Award from the Campbell Collaboration. Welcome, Dr. Tanner Smith.
Well, thank you so much for that introduction, John. And thank you again for the invitation to be here today. So I'd like to start with a brief outline of today's webinar. So I'm going to begin with a high-level overview of meta-analysis and the traditional univariate meta-regression approaches that we often see in the field. Then the majority of today's webinar is going to focus on three modern meta-analytic approaches that can be used to handle multivariate data. So robust variance estimation, network meta-analysis, and meta-analytic structural equation models. And then after a brief summary and recap, we'll have ample time at the end for a Q&A session. So let's first start by defining the concept of meta-analysis. Well, meta-analysis refers to the statistical synthesis or pooling of quantitative findings from two or more primary research studies. And the research studies that we often include in a meta-analysis are typically identified as part of a systematic review, which we can define here broadly as a comprehensive literature review that's conducted in a systematic and reproducible way. So as you can see, as shown in this image here, developed by the Cochrane Consumers and Communication Review Group, meta-analysis refers to the statistical combination or synthesis of findings from multiple research studies. Now, in order to pool the results across multiple research studies, the findings from those studies need to be encoded as effect sizes. And so those effect sizes then are typically used as the outcome or dependent variable in most meta-analytic models. Now, there are many different kinds of effect sizes that can be used in a meta-analysis, depending on the research question of interest. So for instance, in many cases in prevention, we might be interested in the effectiveness of different kinds of programs or treatments. So for instance, we might use standardized mean difference or odds ratio effect sizes to index that treatment effect. But as we'll talk about later today, there are also many scenarios where a correlation coefficient, for instance, may be the effect size of interest if we're interested in summarizing the linear associations between variables. So what's the value of meta-analysis to the field of disease prevention? Well, the current replication crisis that we're experiencing in many social and behavioral sciences today has made it clear that policy and practice decisions generally should not be based on the findings from any single research study, right? So instead, we would hope that evidence-informed decision-making would draw on cumulative summaries of the evidence of the current best available evidence. And so rigorous meta-analyses can provide these cumulative summaries of evidence and can be incredibly useful to decision makers who often don't have the time or the resources needed to cull through these large bodies of research evidence. So meta-analyses can play a critical role in helping advance our science, and they also help us allow addressing research questions that may be difficult or even impossible to address in a single research study. So for instance, through a meta-analysis, we can assess whether findings have been replicated across multiple studies, or perhaps how findings have been replicated or not across different contexts and settings. Now, historically, most frequentist meta-analyses have been conducted using a univariate meta-regression approach, which really just is a mixed effects regression model with heteroscedastic sampling variances. And so this model assumes that we have Y independent effect sizes from I studies, and these effect sizes are assumed to be a function of the true underlying effect sizes in the population, or the thetas. And then we also typically include random effects for studies if we assume that differences in study features may introduce heterogeneity among those true effects in the population. And so that heterogeneity here is represented with the tau squared value. So this very basic meta-analysis model can be used when the goal of a meta-analysis is to estimate the average true effects in the population, as well as variability in those effects in the sample. But, oftentimes we're interested in questions not just about average effects or variability in effects, but we might also want to study how various study characteristics or other moderators, such as the duration of the intervention, might then predict effect size magnitude. And so we can extend these regression models to include one or more predictor variables. Now, of particular relevance to today's topic, the coefficients and standard errors from these meta-regression models are typically estimated using weighted least squares estimation. And in the meta-analytic context, we typically use inverse variance weights, which are the most efficient. And this essentially allocates more weight in the meta-analysis to those studies that are contributing more precise effect size estimates. And those tend in general to be those larger sample size studies. Now, the other important thing to underscore about this approach is that in a univariate context like this, we typically assume that the effect sizes included in the model are statistically independent. And so more specifically, the variance covariance matrix of the observed effect sizes, or the sigma matrix shown here, assumes that the covariances between effects in those off-diagonal elements, we assume that they're zero, right? So we are assuming independent effects. So this traditional meta-regression approach offers an incredibly useful way for us to address questions about average effects and variability in effects, and potentially even explaining or trying to explain some of the variability that we've observed. But there are numerous other meta-analytic methods that we could be using. So my colleagues Sean Grant and Evan Mayo Wilson and I recently guest edited a special issue of the Prevention Science Journal, which was dedicated specifically to highlighting modern but underutilized meta-analytic methods in the area of prevention science. And so this special issue includes tutorial style papers that walk readers through how to use these different methods, but we also included many substantive applications of these methods, so applying these methods to real-world meta-analytic data. Many of the papers in our special issue also included open data and code, which we hope will help facilitate uptake of these methods in the broader community. Now, unfortunately, I don't have time today to talk about all of these methods that we covered in the special issue. So today I'm just going to be focusing on 3 of these methods that, again, are useful for handling multivariate data. So let's expand your meta-analytic toolkit first by discussing robust variance estimation for meta-regression. So as I've already mentioned, traditional univariate meta-regression models assume that the effect size estimates included in the model are statistically independent. But in the real world, right, and particularly in the area of prevention, dependent effect sizes are the norm rather than the exception. Now, sometimes these dependent effects are what we might call multivariate dependent effects, where the sampling errors are correlated because the same participants are represented in multiple effect sizes from the same study. For instance, this often occurs if studies report effect sizes for multiple comparison conditions, multiple outcome measures within the same outcome domain, multiple time points, or even multiple subgroups of participants within a study. But it's also very common for studies to report what we might call nested dependent effects, where the sampling errors of the effect sizes are conditionally independent within studies, but those studies then are nested within some larger cluster, such as a country or geographic region, or even a research lab. Now, there are numerous ways that we can address dependent effect sizes in a meta-analysis. So one naive approach is simply to ignore the dependencies and include all of the effect sizes in the meta-analysis. And as you can imagine, this is generally a bad idea, right? So just as in primary research, when we have clustered data, if we ignore that clustering, then our standard errors are going to be underestimated. And so this is not a good idea. Now, some of the literature, some scholars have distinguished between reductionist and integrative methods that can be used to handle dependent effect sizes. And so these reductionist approaches that could be used essentially reduce the dependent data down to some form of independent data, so that way you can still use these traditional methods. So for instance, a common approach might be randomly selecting one effect size per study to include in the model. Now, these reductionist approaches do eliminate the concern about dependencies in the data, but they throw away data that can be particularly informative, especially if we're interested in those questions about trying to explain potential heterogeneity in effects. And so this is where integrative approaches can be useful because they allow for the inclusion of dependent effects in a single model, but they don't require you to throw away data, right? So there's no loss of data. Now, if the dependent effects that you have in your data are multivariate in nature, and you have information about the underlying dependent structure, then multivariate meta-analysis methods can be used to jointly model those multivariate outcomes. Or if the dependent effects that you have in your data are nested in nature, then multi-level or three-level meta-analyses can be used. But as you can imagine, there are many scenarios where you might have both multivariate and nested dependent effects, or perhaps you don't have any information about that underlying dependent structure. So robust variance estimation is an integrative approach that can be used to handle any of these scenarios. So robust variance estimation with meta-regression, or RVE for short, is one of the most flexible methods for synthesizing dependent effects because it does not require information about the covariance structure between those dependent effects, and it can be used to address multiple or different types of dependent effects. Now, the RVE approach is akin to cluster robust inference methods that many of you are probably very familiar with in the primary research literature, such as Huber-White standard errors or clustered robust standard errors. Now, again, if you remember that pesky variance covariance matrix sigma in our traditional weighted least squares estimator, recall that the problem is that those covariance values and the off-diagonal elements of that matrix are non-zero, right, when we have dependent effects. But the problem is that we often don't know reasonable values of those covariances. Well, the RVE estimator is really innovative because essentially it sidesteps this issue by substituting that sigma matrix with a matrix of cross products of within study residuals that are empirically derived, assuming a working model of the covariance structure. Now, that substitute for the sigma matrix is a poor substitute, right? So it's not a good estimate of the true variance covariance matrix. However, simulation studies have shown that this RVE estimator does perform well as the number of studies increases. Now, the RVE approach uses a working model of the dependent structure. So in other words, an assumed or best guess about that dependent structure. And this working model is then used to identify the weights that are expected to be approximately inverse variance weights, which again are typically the most efficient weights in a meta-analytic context. Now, if the working model is specified correctly, the RVE estimator is fully efficient and the resulting weights are exactly inverse variance weights. But the good news is, even if that working model is misspecified, the RVE estimator will still produce unbiased coefficients and valid standard errors. So in our special issue, James Pustiowski and Elizabeth Tipton presented and expanded upon some of the most common working models that may be of interest to prevention scientists who are interested in using this RVE estimator. So this includes, for instance, the correlated effects working model, which is appropriate for those multivariate dependent effects. They also specified a hierarchical effects working model, which is appropriate for those nested dependent effects. But then they also specified a working model that's a combination of the correlated and hierarchical effects, as well as a working model for correlated effects within subgroups. Now, there are a variety of software packages available to conduct RVE with meta-regression, including some packages in SAS and Stata. But I will say at the present moment, currently the combination of the Metaphor and Club Sandwich packages within R will provide the most comprehensive modeling options for you if you're interested in implementing these methods, particularly with some of these different working models. And that combination of the Metaphor and Club Sandwich packages is also nice because it does allow you to estimate tau squared using the Rimmel estimator, which we know often has better performance than the methods of moments estimators for tau squared, which are implemented in some of those other software packages. So Joshua Polanin and colleagues contributed an article to our special issue that provided a real-world application of the RVE approach. So in this particular meta-analysis, the authors were interested in synthesizing and combining evidence on the effectiveness of cyberbullying prevention programs that were implemented in K-12 education settings. And so the authors were interested not just in estimating the average effects of these cyberbullying prevention programs on bullying outcomes, but they were also interested in examining variability in the effectiveness of these programs across a range of study and participant characteristics. Now, as you can see here in their overall meta-analysis results table, dependent effect sizes were incredibly common in this literature. So many studies were contributing multiple effect size estimates. And because the authors were interested in trying to explain that heterogeneity through moderator analyses, they were hesitant to simply just throw away the data and use some of those reductionist techniques for handling these dependent effects. And so this is why the authors chose to use RVE, and that did allow them to examine and capture all of these data, right, in this comprehensive summary of the best available research evidence. Now, ultimately, I will say the authors didn't find any significant moderators in their confirmatory meta-regression analyses, but nonetheless, this approach allowed them to include all available data and not to have to throw away data using some of those previously mentioned reductionist techniques. So as with any method, of course, there are going to be limitations to be aware of. So the first issue to be aware of is that the RVE estimator does rely on large sample approximations, so can have poor performance if you have small sample sizes, so a small number of studies that you're synthesizing, or if you have effect size moderators that you're interested in examining that have severely unbalanced distributions. And so performance can degrade with those features. Now, another limitation with the RVE approach is that if you misspecify that working model of the dependent structure, because you as an analyst do have to specify that dependent structure, so if you misspecify this, you will get unbiased coefficients and valid standard errors, but in that scenario, it does mean that your estimated heterogeneity parameters, so think about that tau squared parameter, will be imprecisely estimated. And so what this means is that if the working model that you are using in an RVE analysis is likely misspecified, then you should typically refrain from treating those heterogeneity parameters as focal parameters of interest for either description or inference. And then finally, I would say another major caution with this approach is that just because the RVE estimator allows you to include many different kinds of dependent effects in the same meta-analysis does not mean it's appropriate or wise for you to do so. right? And so if you include many different kinds of dependent effects in a given meta-analysis, right, and if you are combining too heterogeneous of evidence in a single synthesis, then that of course can lead to meta-analytic estimates of average effects or slope coefficients that are substantively meaningless, right? So as with any method, it's really essential that analysts think carefully about the sources of dependencies in their data and think carefully about the goals of their analysis before you throw the proverbial kitchen sink into a single model. All right, so let's move on now to the next meta-analytic method that we'll add to your toolbox today, so network meta-analysis. So traditional univariate approaches to meta-analysis, again, can be very useful for addressing questions about a specific pairwise contrast of interest. So for instance, is my treatment better than practice as usual? Is program A better than control? But as prevention scientists, we're often interested not just in these kinds of pairwise comparisons, but we're often interested in the comparative effectiveness of multiple competing interventions that we might use to address the same prevention target. So for instance, if we have 4 programs, program A, B, and C, and D, which of these programs is the best? Well, historically, our ability to assess these kinds of comparative effectiveness questions meta-analytically was often limited by the number of research studies out in the literature that had directly compared all of these programs of interest that we might want to examine. And so this is where network meta-analysis, or NMA, comes in. So NMA models can be used to simultaneously compare the effects of 3 or more competing interventions by combining evidence across a network of studies in a single parsimonious model. And then NMA models can be used to rank the different programs of interest to see which program is most likely to be the best in terms of effect size magnitude. So for instance, the network diagram that you see here is from Evan Mayo Wilson and colleagues, NMA, examining the comparative effectiveness of different interventions for social anxiety disorder in adults. And so the different interventions of interest are represented as nodes or circles in the diagram. And then the solid lines in the diagram show which interventions have been compared directly in the literature. And then the width of those lines is often proportional to the number of studies providing evidence about that specific contrast. Now, I will say that NMA models have been widely used in medicine for over a decade, but they have been relatively underutilized in prevention, which is surprising given their obvious utility for moving beyond, helping us move beyond questions about, does this program work compared to nothing or compared to control? But instead, we often as prevention scientists want to know, well, of these potential programs we could choose from, which of these works best? So one of the appealing features of NMA models is that they allow you to examine direct, indirect, and mixed or combined evidence about the comparative effectiveness of multiple programs within some network. And so direct evidence here refers to pairwise comparisons between 2 programs in the network that have been observed or reported in the literature. So for instance, let's imagine a simple scenario where we might be interested in comparing the effectiveness of 3 programs, A, B, and C, which let's just imagine correspond to motivational enhancement therapy, cognitive behavioral therapy, and psychoeducation programs for reducing alcohol use. Now, as you can imagine, let's say that there are several studies out there in the literature that have directly compared programs A to C, as well as many studies that have directly compared programs B to C. And so these solid lines here are indicating direct evidence, right? Because we have seen these head-to-head comparisons reported in the literature. But as you can imagine, let's say that no studies out in the literature have directly compared programs A directly to program B, right? So we don't have any direct evidence about that contrast. Well, the logic behind NMA models is that under the assumption of transitivity in the network, you can estimate the indirect evidence using mathematical combinations of the direct evidence that is available within the network. So in our very simple example here, the indirect comparison of program A to program B could be obtained by simply taking the difference of the direct comparisons we have for programs A to C and programs B to C. Now, NMA models allow you to then combine the direct and indirect evidence for a given pair of interventions to obtain mixed or combined evidence about that contrast. And so in this very simple example, we could calculate that mixed evidence simply as the inverse variance weighted average of the available direct and indirect summary estimates. Now, a critical assumption behind the calculation of these indirect comparisons is network transitivity, which requires that all of the competing interventions within a network are essentially jointly randomizable. Or stated another way, this transitivity assumption means that we assume that the distributions of any potential effect size moderators are similarly balanced across the different pairs of interventions within the network. Now, the statistical manifestation of transitivity is often called coherence or consistency. And that simply means that the direct and indirect evidence that you have available within a network should generally agree, right? So that they're similar. So the elegance of NMA models then are that they allow you to make comparative statements about different programs or interventions that may have never been directly compared head-to-head in the primary research literature. And so as you can imagine, this offers great promise for informing theory building and theory development efforts. So estimation of NMA models is incredibly straightforward if all of the included studies in your meta-analysis are simply two-arm trials. But as you can imagine, estimating the indirect comparisons becomes more complex when you are synthesizing evidence from multi-arm trials and as the number of interventions in the network increases, right? Because as the size of that network increases, so too does the number of direct and indirect pairwise comparisons you need to make. And so we need a computational model that allows us to pool that data in an efficient manner. Now, there are numerous NMA estimation methods available under both frequentist and Bayesian frameworks. So perhaps the most common applications you'll see are Bayesian hierarchical models, multivariate meta-analysis models, or frequentist graph theoretical models. Now, the important thing to note here is that simulation studies have found that all of these estimations tend to yield the same results with sufficiently large sample sizes. And in both the Bayesian and frequentist frameworks, you can estimate then the relative rankings of the competing interventions within the network. And so we can calculate the ranking probability or the probability that an intervention is at a specific rank when compared to all of those other interventions in that network. So there are numerous software packages that are available for NMA estimation. I will say that I find Geerte Rucker's NetMeta package in R to offer some of the most useful data visualization and graphing options for NMA models. And so that NetMeta package does use a frequentist approach based on methodology from electrical networks and graph theory. So George Sodaitis and colleagues contributed a paper in our special issue, which included a primer and demonstration of how to conduct an NMA using example data from a meta-analysis of brief alcohol interventions for college students. So in this review, there were 9 different intervention conditions in the network of interest, which you can see here in this network diagram. And so that included many name brand programs such as Basics, Alcohol, EDU, and eChug. But as you can see from this network diagram, several of the programs of interest were directly compared in the literature, but there were many other programs that were never directly compared head-to-head in that literature. And so NMA could be useful here by allowing us to estimate not only the direct evidence that's observed in the literature, but also that indirect and mixed evidence in that network. So here are some of the findings from that example paper, and this paper does include open data and open code, so you can go and replicate these findings for yourself. But the image shown on the left here simply shows the combined or mixed evidence for the average intervention effects on drinking outcomes. And these are all displayed here relative to the common reference category of inactive comparison conditions. And then on the right, you can see rankograms from this NMA that show the probability that a given program in the network would achieve a given rank. And again, we had 9 programs of interest here. And so the number 1 rank would be the most effective program, and the number 9 rank would be the least effective program. So in this example, the Thrive and CYD, or Check Your Drinking programs, were most likely to be ranked as the most effective for reducing drinking among college students, whereas the assessment-only control conditions were ranked as the least effective, which is consistent with what we might expect. Now, I also want to briefly mention here another valuable extension to NMA, which is component network meta-analysis, or CNMA. So many of the interventions that we study in prevention are what you might consider complex interventions, right? And so we are often interested in multi-component interventions that have multiple active ingredients or multiple key components embedded within them. Well, CNMA models extend the logic of a standard NMA model and can be used to examine whether, for instance, programs that use component A, for instance, are more effective than programs that use component B or component C, or maybe are they more effective than programs that use components A, B, and C. So in other words, these CNMA models can be valuable for efforts when we are trying to dismantle the effects of multi-component interventions or trying to identify what are the most effective active ingredients within those multi-component interventions. Now, when estimating CNMA models, you do have the option to specify additive or two-way interaction effects, depending on whether you assume those components have independent additive effects, or perhaps whether you think they might have synergistic or antagonistic interactions. Now, CNMA models can be estimated typically using the same software packages as you would be using for NMA. Now, again, there are some limitations of NMA and CNMA models that you should always be aware of, and a lot of this does require careful thinking at the protocol development stage of a meta-analysis. So first, and perhaps most importantly, as I mentioned earlier, the validity of the indirect and mixed evidence in an NMA does require transitivity in the network, and it requires coherence in every loop of evidence in the network. So as you can imagine, the larger the network of interest, the more challenging it can be to meet these transitivity and coherence assumptions. So I would say a critically important part of any NMA is to carefully consider the construction of the nodes that you are interested in that network. And again, it's often wise to attend to that at the protocol development stage, where it's often useful to consult with content experts and other stakeholders to really define those the network of interest, as well as how you're defining the nodes within that network. So similarly, if you broaden a network to include both randomized and non-randomized trials, this can also create some challenges in terms of meeting some of those transitivity and coherence assumptions. And so, for instance, in some cases, it might be more appropriate to estimate your NMA models separately for the non-randomized and randomized evidence if you run into these challenges. But related to this, if you have really sparse networks, then NMA models will often yield imprecise estimates of the effects of interest. And that's where I would say Bayesian methods in particular can be very useful if you do have sparse networks, because you can often specify informative priors that can improve or help that precision in your estimation. Now, another important limitation with the NMA approach is it's always important to remember that the indirect and mixed evidence that you obtain is observational evidence, right? So it is not causal evidence, even if you're only synthesizing evidence from randomized controlled trials. And so just as we do with, when thinking about observational and primary data analysis, we need to be thoughtful about that at meta-analytically as well, and be cautious, considering issues around confounding, for instance. Finally, I do want to remind folks that, these NMA models, right, you're often specifically interested in estimating the relative effects of a pair of programs or pair of interventions within a network. And so because of that, we typically assume homogeneity within those pairwise contrasts within the network. So if you do have a substantial amount of heterogeneity within the comparisons within the network, then you have to be aware, just in a regular meta-analytic context, right, the findings you get from these models may end up, giving you substantively meaningless summary effects if you have quite a bit of heterogeneity. And so in those cases, it obviously is more appropriate to think about conducting NMA meta-regression models, where you can try to model or account for some of that heterogeneity. But I will say that some of those NMA meta-regression models can be computationally intensive and difficult to estimate, particularly if you have a small number of included studies. All right, so the final meta-analytic method that we're going to add to your toolkit today is meta-analytic structural equation modeling. So traditional univariate meta-analysis approaches that we've discussed so far, right, these can be incredibly useful for us if we want to synthesize evidence about correlation coefficients between pairs of variables. So for instance, say we're interested in the linear associations between three variables, x1, x2, and x3. Well, we could use traditional meta-analysis approaches to conduct three separate meta-analyses, right? One meta-analysis that combines the correlations between x1 and x2, a second meta-analysis that combines the correlations between x1 and x3, and then a third meta-analysis combining the correlations between x2 and x3. Now, we could do this, of course, right, doing these three separate meta-analyses, looking at pairs of correlations one at a time, but that approach is incredibly limited, right, because it doesn't respect and it doesn't capitalize on the multivariate nature of these kind of data. So for instance, if we were interested in testing a hypothesized model about how these three variables might relate, so for instance, maybe we're interested in some indirect or mediational pathways as shown on this diagram. Well, if we use that naive approach, that doesn't allow us to test such a hypothesized model. So meta-analytic structural equation modeling then is a useful approach for addressing these kinds of questions, and it does so by combining meta-analysis approaches with structural equation modeling approaches. And by doing so, it allows you to fit and test hypothesized multivariate models using effect size data, right, that you've obtained from multiple studies out there in the literature. Not only does this approach allow you to simultaneously examine the relationships between multiple variables, but it also allows you to test new theoretical models or pathways that perhaps haven't been directly assessed in any primary research study. Now, meta-analytic structural equation modeling is most commonly used in the literature to evaluate path models. And often this is used, for instance, to examine different potential hypothesized causal pathways or mechanisms of action. But it is important to note that meta-analytic SEM models can also be used to fit confirmatory factor analysis models or full structural equation models, obviously just depending on what the research question is and what kinds of data you have available from the included studies. Now, as of today, the best available software to estimate these Meta-SEM models are in Mike Chung's Meta-SEM R package. I will say there's also a recently released web-based Shining app, which I've noted here, which might also be of interest, especially as you're starting to get familiar with these tools. Now, there are two different flavors of meta-analytic structural equation modeling that I am going to briefly cover here. So the first flavor of this method has been called two-stage structural equation modeling. And as the name implies, this approach involves two stages of estimation. So at the first stage, you would estimate a pooled or meta-analytic correlation matrix that combines the findings from all of the study-specific correlation matrices that you've collected. And so this first stage simply involves conducting an inverse variance weighted multivariate meta-analysis model and typically using maximum likelihood estimation. So after the pooled or average correlation matrix is estimated in that first stage, the second stage then involves fitting a structural equation model to that pooled correlation matrix and its asymptotic sampling covariance matrix. And I would say one of the nice features of this method is that it can accommodate missing correlations within any matrix from a study, and it can accommodate those missing data using full information maximum likelihood. So in this two-stage structural equation model, weighted least squares estimation is used to fit the structural equation models, And then, the resulting output that you get the standard likelihood ratio tests, goodness of fit statistics, right, that you can use to evaluate model fit. And just as we do with SEM and primary research, these meta-SEM models allow you to test, the equality of coefficients, allow you to test for indirect effects. And this two-stage model also allows you to examine the effect of one categorical effect size moderator at a time, and it does so using a multiple group SEM approach. Now, that last reason, right, so this two-stage approach only allows you to include one categorical moderator at a time. And so this is why the need arose for a second flavor of meta-SEM models, which are one-stage meta-analytic structural equation models. And so as the name implies, this flavor of meta-SEM is technically only conducted in one step, but the general concept is the same. So in this one-stage approach, the structural equation model is fit directly on the primary study data, essentially treating each study as a participant, like we would in a traditional SEM model. So the vector of correlation coefficients and then their variance component are then modeled as the mean and covariance structures in the SEM. So you can think about this method as really only occurring at the first stage, but that pooled correlation matrix is restricted to adhere to the structure of the hypothesized structural equation model. Now, importantly, the one-stage and two-stage approaches here will produce similar results. But where the one-stage models are perhaps most useful and promising for prevention scientists is that the one-stage models do allow you to include multiple moderators at any level of measurement. And so you don't have to artificially dichotomize your moderators in order to use them. So moderators can be continuous or categorical, and any of the parameters in the SEM model can be modeled to interact with those potential effect modifiers. And so again, that's one really unique benefit of the one-stage approach is that it does allow you to examine multiple moderators, but also continuous moderators. Now, one of the papers in our special issue provided a tutorial, an example of how to apply both the one and two-stage meta-analytic structural equation models. So in this paper, Jeffrey Valentine and colleagues used the meta-SEM approach to examine whether dysfunctional attitudes might mediate the effect of automatic thoughts on depressive symptoms, as shown in this diagram here. And so the authors were able to estimate the path coefficients for the model, and then they were able to examine whether these A, B, and C paths might be moderated by several sample characteristics. Now, the path model that they examined in this tutorial paper was simplistic, intentionally for the purposes of illustration. But as you can imagine, the meta-SEM method can be used to test even more complex theorized pathways. So for instance, Martin Hager and colleagues recently published a meta-SEM paper in Health Psychology that tested an underlying proposition of the theory of planned behavior, which is that people are more likely to act on their behavioral intentions and report intentions aligned with their attitudes and norms when they have high levels of perceived behavioral control. And so the image shown here shows those hypothesized relationships of interest, including that potential moderating effect of perceived behavioral control. And so the authors were able to examine this hypothesized pathway using one-stage meta-SEM models, and you can see some of the results here. Now, again, although both of the examples that I've just shown have used meta-SEM applications for path models, again, it is possible to use these methods to address CFA or full SEM model questions using meta-analytic data. Now, again, there are limitations to the meta-SEM approach that you want to be aware of. So first, and I realize I probably sound like a broken record here, but these methods generally have poor performance with smaller sample sizes, particularly if the number of included studies is less than 30. So that is an important consideration to keep in mind. Another issue to consider is that the FIML method that's used to address missing data, if you have missing correlations from any given study, that FIML method does assume that the missing data are assumed to be missing at random or missing completely at random. And so that often might be a reasonable assumption in some contexts, but if the missing data are missing not at random, then the methods will yield biased estimates. So just as with any method, right, it's important for us to think carefully about the mechanisms of missingness before we just use these approaches without thinking about it. Another important consideration, I don't know if it's a limitation, but just something to keep in mind, is that in these methods, the pooled correlation matrix on which you are applying, this SEM model, may not actually provide a realistic reflection of the actual correlation matrix in any given study in the literature. So again, this is something to think about carefully, particularly at the protocol development stage. And then finally, I would say another important limitation to the one-stage meta-SEM approach in particular is that the method does not allow you to quantify the heterogeneity of the SEM parameters. For instance, if you want to know the amount of variance explained, on a certain pathway. But rather, this method only allows you to quantify the heterogeneity in the correlation coefficients. Now, again, that's often what we are most interested in. But if you are interested in quantifying the heterogeneity of the SEM parameters themselves, then that's where you would need to use typically Bayesian meta-SEM approaches to address those kinds of questions. Okay, so we've now covered 3 modern but underutilized meta-analytic methods that may be useful to add to your toolbox. So as I've discussed today, these recent methods are now widely accessible via freely available software and packages, and our special issue included many tutorials and open code and open data so that you can get familiar with these methods and hopefully maybe apply them to the kinds of complex types of questions and complex types of data that you might be facing in your own meta-analyses. Right, so robust variance estimation can assist when you're analyzing, right, these messy, complex, dependent data structures that we often face when we are doing meta-analyses of prevention evidence. Then network meta-analysis and component network meta-analysis methods can be used to address questions about comparative effectiveness, right? And these kinds of comparative effectiveness questions are incredibly important to decision makers, particularly when they're faced with, selecting programs, from a menu of options, right? When they have to allocate scarce resources to the different programs. And then finally, the meta-analytic structural equation models that we talked about can be incredibly useful for examining, testing, building, and expanding upon our theories underlying the kinds of interventions and prevention efforts that we're undertaking. So again, for anybody who is interested in learning more about these techniques, I'd highly recommend you check out our recent special issue in the Prevention Science Journal on this topic. And also there are several key readings and references that will be included in this slide deck as well. And so that will be a great place for folks to start. So with that, I think we can stop here and open it up for questions.
Great, thanks so much, Dr. Tanner Smith. Yes, we've had a lot of questions roll in. So I guess during the presentation, and certainly questions can continue to be asked in the chat. But yeah, go ahead and get started with some of these. So just kind of maybe as a more general question, you mentioned there's lots of software available for doing these analyses. Is syntax available at any particular site? I know R certainly has good documentation. Sorry, go ahead.
Yeah, absolutely. And so that's a great question, right? Because, again, our hope is that folks will use these in order to use these methods, right? It is very helpful to have the syntax. So I will say that all of the, and I will just admit my bias that I'm most familiar with the R packages, but I would say all of the R packages, right, tend to have reasonably good documentation. And then, so I would say, obviously, that's a first place to start is with the packages that I've named here. But then I would say that the special issue papers that we had, most, if not all of them, have open data and code. And so if you go to those articles, I think most folks have archived their code on OSF, so the Open Science Framework, and so you can download that. And so that can be helpful because not only do you have documentation there, but you've got some example data and you can see and walk through those examples with that open code. So I do think there is ample documentation available for folks who are interested. There's not a one common repository for that, but that's an interesting concept, because again, many different scholars are creating these packages, and so they typically have their own documentation. But absolutely, I think all of these packages that I've cited in the text have good documentation out there. And then I would say, start with some of the tutorial papers in our special issue, and then maybe some of the key references that I've included here often will have example code as well.
Great, thanks. Talking about RVE, robust variance estimation. So one question was asked, is there a way to assess if the working model is misspecified or not? Is there a way to choose the best working model for RVE?
Yeah, so that's a great question. And so in terms of, there aren't any formal statistical tests that you would conduct to see, have you misspecified the model, but really the specification of the working model is going to be driven by your understanding of where the dependent effect sizes are coming from. And so that is something that you will know because you've collected those dependent effects from the literature. And so again, it's, what you will be thinking about is, do you have those multivariate dependent effects, right? Which is where you've got correlated sampling errors because the same participants are represented in multiple effect size estimates. I will be honest that the vast majority of the meta-analyses that I've conducted in prevention science, multivariate dependent effects are the kinds of dependent effects we have the most often, right? Because researchers might report multiple outcome measures that really represent the same outcome domain. So for instance, if you're interested in alcohol consumption as an outcome, there might be many different ways that authors have reported and operationally defined alcohol outcomes. And so they might report 5 different alcohol outcome effect sizes. And so because you've collected those data, that they're multivariate in nature. I would say that in psychology, you might run into more nested dependent effects where you do have independent effects within studies, but then those studies might be nested within larger units that you care about, such as country or region or funding agency or research group, those sorts of things. So again, in terms of knowing whether you've specified that working model correctly really depends on you knowing where those dependencies are arising from. So are they coming from studies reporting multiple outcomes? Are they coming from studies reporting multiple time points for the same sample of participants, or are these larger clustering kinds of questions? So I will say that the Pustiovsky and Tipton paper in our special issue does an excellent job of laying out what I consider probably the working models that would cover 95% of the cases we see in prevention science today. And so I would definitely encourage you to take a look at that, and they walk through these carefully. But again, the assurance is that even if you misspecify that working model, your coefficients and standard errors are going to be good. But again, you would want to just tread carefully if you think you've misspecified it. Really think about those heterogeneity parameters.
Okay, great. Ask a question about network meta-analysis now. So there's a couple key assumptions for transitivity and coherence. Is there a way to test those, and if you happen to find incoherence in the network, is there anything that can be done to address it?
Yes. Oh my gosh, this is such a good question, because really I think this is one of the challenges, and I think this is probably one of the reasons we haven't seen NMA being uptaken by the community and used more often, is just the difficulty of this assumption, often in some of the social and behavioral science scenarios that we find ourselves working in. So yes, there are statistical techniques that you can use to assess. Well, so there are statistical techniques and conceptual techniques that you can use to test and assess the viability of the transitivity assumptions and the coherence assumptions. And so I will say that the Sodaitis et al. Tutorial paper in our special issue does a really nice job of walking through the different tests that you can use. And so they provide example code for all of those tests, and you can do those kind of at the local level within loops, or you can assess kind of global incoherence in the full network. So definitely check that out for those specific statistical tests you can use to kind of diagnose and assess this. But then I think the more challenging thing is then what do you do, right, when you find incoherence or inconsistence? So the first thing I would say is, just as with any data analysis, the first thing you want to do is actually, go and make sure there aren't any, data entry errors or other kind of errors that are, artificially creating this incoherence, right? So you double checking the data. But then I would say a lot of this is then taking a step back and thinking carefully about your inclusion criteria for what kinds of studies you're including in the meta-analysis and the NMA, and then also thinking carefully about have you been too broad in the definition of nodes within the network, right? So what is considered a node that's being compared in the intervention? So in the social sciences, I think one of the trickiest issues that we run into is how do you define those comparison condition nodes, right? Because if treatment as usual looks different in the literature when it's compared to program A versus when it's compared to program B, then that's essentially violating this assumption of transitivity. And so in some cases, for instance, you might have multiple nodes for different kinds of comparison conditions. So in the Sudaitis et al. Article, for instance, they ended up including, a node for active comparison conditions and a node for inactive comparison conditions. But you might even need to go a step further. Maybe you've got a separate node for waitlist controls, a separate node for placebo controls, a separate node for sham treatments or interventions. And so again, sometimes you need to really think, is there too much heterogeneity in the definition of the nodes that could be leading to the violations of the assumptions? So I would say a lot of this, prevention is, an ounce of prevention is worth a pound of cure. I think that resonates with this audience. And so this is why, again, at the protocol development stage, it's really important to think about these issues, talk with stakeholders, talk with content experts, to think carefully about, is transitivity going to be a reasonable assumption in this network? And then how are we defining these nodes? And then, of course, last resort efforts, sometimes it's impossible, right, to find coherence in a network. And so in some scenarios, you might end up, for instance, splitting the network into multiple subnetworks of interest, right? So then you could actually get coherence in those subnetworks. Or you might, for instance, try to use some of those network meta-regression approaches to try to account for, explain some of that potential variability that might be leading to some of that excessive incoherence.
Thank you. And question about meta-analytic SEMs. So does the one-stage meta-analytic MASEM allow for nested data, like nested within program? Can you represent those sorts of types of data with the model?
Yeah, so that's a really excellent question. So as of today, the one-stage meta-SEM implementation that is available in that R package essentially does not allow you to address those nested data, right? Which is really problematic given what we just talked about, which is that nested data are much more frequently, present in the kinds of data that we work with in prevention science. So what I will say is that I think this is an important area for future research. And so there are brilliant minds out there working on this as we speak. But I will say that, the way that folks are often kind of attending to these issues of nested data is perhaps using the two-stage approach. And then essentially at that first stage of the two-stage meta-SEM, then you can use something like multi-level meta-analysis or robust variance estimation to handle those dependencies in the data. And so historically, that's how folks have addressed this, is really addressing it in stage one. At present, there's not a great way to do that within the existing packages, but I think this is an important direction for future research when we think about the kinds of complex, messy data that we so often observe in the field of prevention.
Definitely. I think we probably have time for one more question. So question, I think this is maybe a more general to the meta-analysis question. So when we talk about sample size in a meta-analysis, that may mean the number of studies in the analysis, but sample sizes per study could have variable size, maybe something extremely small or large. How in meta-analysis is the size of individual samples handled? How does that play a role in the analysis?
Yeah, that's a great question. So yeah, when I was, saying all of the potential things to be aware of, right, with these methods and their performance, right, and that is typically tied to the number of included studies, right. That's the sample size that is driving a lot of our statistical power in a lot of these methods. But you are absolutely right that the sample size of the primary studies is also really important. And so where that plays a role in meta-analysis is really through the weights, right? And so again, in most meta-analytic contexts, we will use inverse variance weights because those are the most efficient. And those inverse variance weights, again, are often giving more weight to the larger sample size studies and then giving less weight to the smaller sample size studies. I mean, that is an oversimplification, but in general, that's where the information goes into, right? And you think about that weighted least squares estimator, right? Those weights are included there. And so essentially that's where we take into account the different levels of precision we'll have from large versus small sample size studies.
Great. Well, thank you very much, Dr. Tanner Smith, and thank you to everyone who participated in today's webinar. On the Mind the Gap website, prevention.nih.gov/mindthegap, you'll find several resources for this talk, including the slides and a list of references. We will also be posting a recording of today's webinar on our website in a few weeks. Thank you and have a great rest of your day.